Okay, now we can consider a standard macroeconomic model, very simple macroeconomic model, in which we have two equations. The first equation is aggregate consumption, in which the aggregate consumption is equal to C0 plus C1y, where C1 is between 0 and 1. C1 is the so-called propensity to consume, and is between 0 and 1 because if C is aggregate consumption, this in our hypothesis can be explained by income through the propensity to consume. So Y is income. If income goes up, also consumption goes up. And 0, which contains or represents all variables other than income that can explain consumption. So, for instance, total wealth or interest rate. The second equation of our model is the equilibrium equation, which the income produced in this economy in equilibrium must be equal to the aggregate demand, which in this very simple model is given by the consumption plus the government expenditure G. Now in this model we have two endogenous variables, which are consumption and income, and we have two exogenous variables, which are the so-called the government expenditure and C0, which is the so-called which represents all variable affecting consumption other than income. So we can write endogenous variable Y and C, and we have to determine these two variables respect to exogenous variable, which are C0 and G, because our aim is to consider the effect of an increase in C0 or in G, which is a political economy, because if government increase public expenditure, this is a political economy for the government. It is the tool by which the government can influence income and consumption. And also C0, which is part of consumption which is not explained by income. Now we can write the system in the following way. We can call C star in order to understand that is the equilibrium value of consumption, minus C1 Y star equal to C0. So we put on the left hand side Y. And we have the second equation, Y star minus C star equal to G. Y star and C star are the endogenous variable we want to determine. Now we can write in a matrix form this system. We have matrix A, which is defined as matrix of coefficient of endogenous variables. We have two equations and two endogenous variables, and the coefficients are 1 minus 1, 1 minus 1. And we have the vector of endogenous variables, which is composed by Y star C star. Matrix B equal to 1, 0, 0, 1, and vector of exogenous variable, which is, it's better to put three lines in order to define a matrix or a vector. The vector x is given by the exogenous variables, which are C0 and G. In this way we can write this system as AY equal to Bx in matrix form, in a more compact form, and we can find the solution Y for our endogenous variable vectors as the inverse of matrix A, so two lines, times B times X. So we need to compute the inverse of matrix A, or matrix of coefficient for endogenous variables. Now, in order to compute the inverse matrix, we can write matrix A. Matrix A is defined as minus 1, 1, 1, minus 1, yes. Now we have to consider matrix of cofactor for matrix A. So cofactor for minus C1 is minus 1 with the same sign, because it's in the position 1, 1, so the sum is 2, and minus 1 to the power of 2 is plus 1. And we have the cofactor 1, which is minus 1, no, because we need to change the sign of these elements, because 1 is in position 1, 2, so the coefficient is minus 1 to the power of 3, which is minus 1, so we need to change the sign. The same when we consider the cofactor of these elements is minus 1. Finally, the cofactor of this element is minus C1 with the same sign, because it's in the position 2, 2, which is minus 1 to the power of 4 is equal to 1. Now we need to consider the so-called joint matrix, which is given by the transpose of matrix of cofactor. So it's given by minus 1, minus 1, minus 1, minus C1. This is a joint matrix. The first row becomes the first column, and the second row becomes the second column. And we can write now in order to we need to compute the determinant of matrix A. This is equal to, applying the rule, the product of the elements along the main diagonal is equal to C1 minus the product of the element on the second diagonal is minus 1. So this is the determinant. So C1 must be other than 0, because in order to compute the inverse of matrix, the determinant must be other than 0. And now the inverse of matrix A is given by what? By the adjoint matrix times 1 over determinant of A. So we can write this inverse matrix A as 1 over 1 minus C1, again 1 over 1 minus C1, again 1 over 1 minus C1, finally C1 over 1 minus C1. We can also check that this inverse matrix is correct, computing the product between A and A minus 1. You can do it by yourself, because you are able now to do this product. This must be equal to the product of A minus 1 times A, and must be equal to the identity matrix. I remember you, this is the matrix 2 by 2, 1, 1, 0, 0. So with elements equal to 1 on the main diagonal and to 0 on the second diagonal. Now we can delete this vector. We can solve the system. You know that y is equal to, in matrix form, A minus 1 inverse of matrix A times B times X. So we can write in matrix form in the following way: y is given by the vector y star c star, the equilibrium value for income and consumption, must be equal to the inverse of matrix A, which is 1 over 1 minus C1, again 1 minus C1, 1 minus C1, C1 over 1 minus C1. Matrix B is given by 1, 0, 0, 1, and the exogenous variables are C0 and G. So we need to consider this. Multiply these first two matrices, we get the final solution of our system, and then we can multiply by this, or we can multiply these two matrices and then we can multiply by the first matrix. The final solution of this system will be my star equal to multiply this first row by this first column. We can also rewrite this is in vector form the following way, because if we multiply these two matrices, this is an identity matrix, so we get the matrix A. So we can write as 1 minus C1, 1 over 1 minus C1, 1 over 1 minus C1, C1 over 1 minus C1, which multiply C0, G, which are the two exogenous variables. Now we can write the final solution of our system, y star equal to 1 over 1 minus C1 C0 plus 1 over 1 minus C1 over G, and this is obtained by multiplying this row by this column. C star will be equal to 1 over 1 minus C1 C0 plus C1 over 1 minus C1 G, and this is the final solution of our model, or the reduced form model. Now we can see the effect of an increase in the government expenditure on income and on consumption, the final equilibrium effects. So if we have an increase in the public expenditure, we have also an increase in income, which is but considering the effect is given by this coefficient, which is a number greater than 1. It's the so-called multiplier effect, because C1 is smaller than 1, so this ratio is greater than 1. And so if we have an increase in the government expenditure greater than 100, equal to 100, the increase in income will be greater than 100, maybe 200, 300, and this very simple model, this fact is due to the size of C1, of the propensity to consume. But if we have an increase in public expenditure G, we have also an increase in consumption, in the equilibrium consumption, but this increase is smaller than the increase we have in income, because if we're increasing in income, the increase in consumption is due to the propensity to consume, but is just a proportion, is just a part of the increase in income. For instance, 80%. We can imagine that C1 is equal to 0.8, so 80%. This reduced form model shows also that an increase in C0, which is the expectation, we can think that C0 is the expectation of households for future. So if we have an increase in C0, we can see an increase in income, and the entity of this increase is due to this coefficient, that is a number greater than 1, and the same number gives an increase to the final consumption. So this is a useful, very simple useful model, but it's very useful to show the utility we can derive from the mathematical tool we have explained before. Now we need to consider also nonlinear system, but in order to consider a nonlinear system, we need to introduce differential calculus.